Have you ever wondered what secrets the universe still hides? Tonight we'll drift through some of its greatest mysteries, unanswered questions about time, space, and the strange forces shaping everything we know. As the story unfolds, you won't need to keep up, just let your mind wander. And once the narration ends, a deep, calming sound called brown noise will carry you through the night. It's a soft, low-frequency hum designed to quiet your thoughts and keep you in restful sleep. Close your eyes and imagine floating in the vast darkness of space, weightless and serene, surrounded by the gentle glow of distant stars. There is something profoundly calming about contemplating the universe at night, letting your mind drift among cosmic mysteries that have puzzled humanity for millennia. These are not urgent questions demanding immediate answers, but slow, patient puzzles that have waited billions of years and can wait a little longer. Tonight, let us wander together through some of the most beautiful and mysterious phenomena in our cosmos, not to solve them, but simply to appreciate their quiet grandeur, to let their gentle mysteries wash over us like waves on a distant shore. The universe is old, so incredibly old that human timescales become meaningless when we try to comprehend its age. 13.8 billion years have passed since the beginning of everything we know. Imagine that span of time stretching out behind us like an endless ocean. In that vast expanse, stars have been born and died, galaxies have formed and merged, planets have condensed from cosmic dust and evolved complex surfaces. And yet, despite this immense age, the universe is still young in cosmic terms. Stars will continue to shine for trillions of years into the future. The universe has barely begun its long, slow journey toward whatever ultimate fate awaits it. There is something deeply restful about this perspective. Whatever happens in our brief lives, whatever worries keep us awake at night, they are infinitesimally small ripples in the vast ocean of cosmic time. The stars shining tonight have been shining for millions or billions of years before we were born, and they will continue shining long after we are gone. This is not meant to diminish the importance of our lives, but rather to place them in context, to remind us that we are part of something much larger and older than ourselves, something that continues with patient indifference to our individual struggles. Consider the light from distant stars. When you look up at the night sky, you are not seeing the stars as they are now, but as they were when their light began its journey toward Earth. The light from Proxima Centauri, our nearest stellar neighbor, takes about 4 years to reach us. We see it as it was 4 years ago. The light from more distant stars has been traveling for decades, centuries, even millennia. When you look at the Andromeda Galaxy, that faint smudge of light visible on dark nights, you are seeing it as it was 2.5 million years ago, when our ancestors were just beginning to walk upright on the African savanna. This means that when we look at the night sky, we are looking back in time. The universe presents itself to us not as it is, but as it was, layer upon layer of history written in light. Every photon that enters your eye is a messenger from the past, carrying information about events that happened long ago in places impossibly far away. The night sky is not a snapshot of the present, but a deep archive of cosmic history, with different stars and galaxies representing different moments in the universe's long story. There is something meditative about this realization, about understanding that the light touching your retina now has been traveling through empty space for longer than human civilization has existed. Let us drift now to one of the most serene mysteries of the cosmos, the cosmic microwave background radiation. This is light that has been traveling through space for nearly the entire age of the universe, about 13.8 billion years. It was released when the universe was only 380,000 years old, a brief moment after the Big Bang, when the cosmos had cooled enough for atoms to form and light to travel freely for the first time. Before this moment, the universe was so hot and dense that light could not travel far without being absorbed and re-emitted. The universe was opaque, like being inside a star. But as the universe expanded and cooled, it reached a point where electrons and protons could combine to form neutral hydrogen atoms. Suddenly, light could travel freely through space. The universe became transparent. The light released at this moment has been traveling ever since, stretched and cooled by the expansion of the universe, shifted from visible light into microwaves. This ancient light fills all of space, a faint glow with a temperature of about 2.7 degrees above absolute zero, the cooled remnant of the hot early universe. When scientists map this cosmic microwave background, they see tiny temperature variations, regions that were slightly hotter or cooler when the light was released. These variations are incredibly small, just a few parts in 100,000, but they are profoundly important. They represent quantum fluctuations from the very early universe, tiny random variations in density that were stretched to cosmic scales by cosmic inflation. These small variations were the seeds from which all structure in the universe grew: galaxies, stars, planets, us. There is something almost mystical about the cosmic microwave background. It is a message from the beginning of time, a snapshot of the universe in its infancy, preserved and delivered to us across billions of years. When you tune a radio between stations and hear static, a small fraction of that noise, about 1%, is actually the cosmic microwave background, the afterglow of creation itself washing over your antenna. You are literally listening to the echo of the Big Bang. This ancient light bathes us constantly, invisible but always present, connecting us to the very origin of the cosmos. Imagine lying under the stars on a warm summer night, looking up at the Milky Way stretching across the sky like a river of light. Our galaxy contains hundreds of billions of stars, but what you see with the naked eye is just a tiny fraction of them, the nearest and brightest. Most of the galaxy is hidden from view, obscured by dust, or simply too faint and distant to see without telescopes. Yet even what we can see is breathtaking. That band of light is our view from inside the galactic disk, looking through the thickness of the spiral arms toward the galactic center. The Milky Way is ancient, formed more than 13 billion years ago in the early universe. It has evolved over cosmic time, growing through mergers with smaller galaxies, forming new stars from clouds of gas and dust, losing old stars to stellar death. The Sun itself is a relatively young star, only about 4.5 billion years old, formed from material enriched by previous generations of stars that lived and died before our solar system existed. We are made of stardust. Literally, the atoms in our bodies were forged in the nuclear furnaces of long-dead stars and scattered into space when those stars exploded. There is a gentle profundity to this realization. We are not separate from the cosmos, but intimately connected to it. The carbon in our cells, the oxygen we breathe, the iron in our blood, all of these elements were created inside stars. We are the universe experiencing itself, matter organized into patterns complex enough to contemplate their own origins. This is not mysticism, but scientific fact. The same physical processes that govern the stars govern our bodies. The same atoms that float in interstellar space are the atoms we are made of. We are continuous with the cosmos, not isolated observers, but participants in its ongoing story. Let your mind drift now to the space between the stars, the vast emptiness that separates solar systems and galaxies. We call it empty space, but it is not truly empty. It is filled with fields, electromagnetic fields, gravitational fields, quantum fields that pervade all of reality. These fields are more fundamental than particles. Particles are just excitations of fields, ripples in the underlying fabric of space-time. An electron is a ripple in the electron field. A photon is a ripple in the electromagnetic field. Even empty space devoid of particles still contains these fields, vibrating with quantum fluctuations, spontaneously creating and destroying virtual particle pairs that exist for infinitesimal moments before annihilating. The quantum vacuum is not nothing but a seething foam of activity at the smallest scales, a realm where the certainty of classical physics breaks down and is replaced by probabilities and uncertainties. Particles can borrow energy from the vacuum, existing briefly before repaying the debt, allowed by Heisenberg's uncertainty principle, which says that energy and time cannot both be precisely determined simultaneously. The vacuum itself has energy, what physicists call vacuum energy or zero-point energy, the energy of empty space at its lowest possible state. This energy is real and has measurable effects, like the Casimir force that makes two uncharged metal plates attract each other in a vacuum. There is something paradoxically restful about the concept of quantum uncertainty. At the deepest level, reality is not deterministic, but probabilistic. The future is not fixed, but emerges from a cloud of possibilities. Quantum mechanics tells us that particles exist in superpositions of states until measured, that the act of observation affects what is observed, that there are fundamental limits to how precisely we can know certain pairs of properties simultaneously. This might seem unsettling, but it also means that the universe is not a clockwork mechanism grinding toward a predetermined end. It is creative, spontaneous, genuinely open to novelty. Consider the phenomenon of quantum entanglement, one of the strangest and most beautiful features of quantum mechanics. When two particles interact and then separate, they can remain connected in a profound way. Measuring the state of one particle instantly affects the state of the other, no matter how far apart they are. This is not because of any signal passing between them. No information travels faster than light. Rather, the two particles share a single quantum state, a correlation that transcends space and separation. They are, in a sense, a single system, even when light years apart. Einstein called this spooky action at a distance, and thought it revealed a flaw in quantum mechanics. But experiments have confirmed that entanglement is real. Particles can be correlated in ways that no classical theory allows, connected through quantum links that persist across arbitrary distances. This suggests that the universe is more interconnected than our intuitions suggest, that separation and distance are not as fundamental as they appear. At the quantum level, particles that have interacted remain part of a single, unified system. The boundaries between here and there, between separate objects, become fuzzy and ambiguous. There's a meditative quality to this insight. What seems separate might be deeply connected. The boundaries we perceive are not absolute, but approximate, useful for navigating the everyday world, but not reflecting the deepest structure of reality. Quantum mechanics reveals a universe that is holistic, where parts are connected to wholes in ways that transcend space and time. This is not mysticism but physics, confirmed by rigorous experiments and precise mathematics. Yet it has a contemplative beauty, suggesting that isolation is an illusion, that everything is part of a larger, interconnected whole. Let us turn now to the great cosmic cycles, the slow rhythms of stellar birth and death that play out over millions and billions of years. Stars are born in vast clouds of gas and dust called molecular clouds, regions where gravity slowly pulls matter together until densities and temperatures become high enough for nuclear fusion to ignite. A star is born in light and heat, beginning a life that will last millions to trillions of years depending on its mass. During this life, the star will fuse hydrogen into helium in its core, releasing enormous amounts of energy that keep the star shining and prevent it from collapsing under its own gravity. Massive stars burn hot and bright, exhausting their fuel in just a few million years before exploding as supernova, scattering heavy elements into space and leaving behind neutron stars or black holes. Medium-sized stars like our sun burn more slowly, lasting about 10 billion years before swelling into red giants, shedding their outer layers and leaving behind dense white dwarf cores. Small stars, red dwarfs, burn so slowly that they can last for trillions of years, longer than the current age of the universe. None of the red dwarfs that have ever formed have yet died of old age. They will continue shining long after stars like the sun have gone dark. There is something profoundly patient about stellar evolution. Stars take their time. They burn steadily for eons, indifferent to the brief lives of planets and civilizations. The sun has been shining for 4.5 billion years, and it will continue for another 5 billion before entering its red giant phase. In human terms, this is eternity. The sun that warmed the dinosaurs is the same sun that shines on us today, unchanged in any way we could detect. It will shine on whatever creatures inherit the earth long after humans are gone. Stars are anchors of stability in a changing universe, constants against which the rapid changes of planetary surfaces and biological evolution play out. When a massive star exhausts its fuel, it can no longer support itself against gravity. The core collapses catastrophically, reaching densities and temperatures so extreme that protons and electrons are crushed together into neutrons. The collapse rebounds in a supernova explosion, one of the most violent events in the universe, briefly outshining an entire galaxy. What remains is a neutron star, a sphere about 20 kilometers across, containing more mass than the sun, made entirely of neutrons packed together at nuclear densities. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. Neutron stars are strange objects, extreme in ways that challenge our understanding. Their magnetic fields are trillions of times stronger than Earth's. They can rotate hundreds of times per second, their surfaces moving at significant fractions of the speed of light. Some neutron stars, called pulsars, emit beams of radiation from their magnetic poles, and as the star rotates, these beams sweep across space like a lighthouse. If Earth happens to lie in the path of the beam, we detect regular pulses of radio waves or light, ticking with metronome precision. Pulsars are among the most accurate clocks in the universe, some varying by less than a microsecond per year. The discovery of pulsars in 1967 was initially so puzzling that astronomers jokingly called the first one LGM-1 for Little Green Men, wondering if the regular pulses might be artificial signals from an alien civilization. But the signals were too fast and too regular to be artificial. They were natural phenomena, the lighthouse beams of rotating neutron stars, predicted by theory but never observed until Jocelyn Bell Burnell detected them in radio telescope data. The universe had revealed another of its secrets, showing us objects so extreme that they existed at the very edge of what matter can be. Beyond neutron stars lie black holes, objects so dense that not even light can escape their gravitational pull. A black hole forms when a massive star collapses completely, crushing matter into a region of infinite density called a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape. Black holes are invisible by definition, detectable only through their gravitational effects on nearby matter and light. They warp spacetime so severely that the normal rules of geometry break down. Inside the event horizon, space and time swap roles. Just as you cannot avoid moving forward in time outside the horizon, you cannot avoid moving toward the singularity once you cross it. Black holes represent a mystery at the intersection of quantum mechanics and general relativity, a place where our current theories break down. Inside the event horizon, quantum effects should become important, but we don't yet have a theory of quantum gravity to describe what happens. The singularity at the center of a black hole is a place where densities become infinite, where the curvature of space-time becomes infinite, where our equations produce nonsensical results. This suggests that our understanding is incomplete, that there is deeper physics we have not yet discovered. Yet black holes also have a serene quality. Once matter crosses the event horizon, it is gone from the outside universe forever. Information appears to be lost, though this creates paradoxes that physicists are still working to resolve. From outside, a black hole is eternal and unchanging, a region of perfect darkness. Nothing dramatic happens at the event horizon for a distant observer. Matter and light simply disappear, swallowed by gravity. There is a finality to it, a boundary beyond which we cannot see or communicate. The universe has secret regions that are permanently hidden from us, interior spaces that are causally disconnected from the rest of reality. Stephen Hawking discovered that black holes are not entirely black. Through a quantum process now called Hawking radiation, black holes slowly evaporate, losing mass and energy over immense timescales. The smaller the black hole, the faster it evaporates. Stellar mass black holes take longer than the current age of the universe to evaporate significantly. Supermassive black holes, millions or billions of times the mass of the Sun, will take googolls of years, 10,100 years and more, to evaporate completely. But eventually, all black holes will evaporate, leaving behind only faint radiation. Even these seemingly eternal objects are temporary on cosmic timescales. Let your thoughts drift now to the gentle expansion of the universe itself, the slow stretching of space that has been occurring since the Big Bang. The universe is not static, but dynamic, growing larger with every passing moment. This expansion is not like an explosion where matter flies outward into empty space. Rather, space itself is expanding, carrying galaxies along with it. The distances between galaxy clusters grow over time, not because the galaxies are moving through space, but because the space between them is stretching. This expansion was discovered by Edwin Hubble in the 1920s when he observed that distant galaxies are moving away from us, and the farther away they are, the faster they recede. This is not because we are at the center of the universe. The same pattern would be observed from any galaxy. It is a property of the expanding space itself. Imagine dots on the surface of a balloon. As you inflate the balloon, every dot moves away from every other dot, and dots that are farther apart move away from each other faster. This is analogous to how galaxies move in the expanding universe. The expansion has been occurring for about 13.8 billion years, and it will continue forever. But the rate of expansion is not constant. In the universe's early history, it was expanding very rapidly, slowing down over time as gravity pulled matter together. But about 5 billion years ago, something remarkable happened. The expansion began to accelerate. The universe is not just expanding, it is expanding faster and faster over time. This acceleration is driven by something called dark energy, a mysterious form of energy that fills all of space and pushes space apart. Dark energy is one of the deepest mysteries in cosmology. We don't know what it is. It doesn't behave like normal matter or energy. It doesn't clump together gravitationally or interact with light. It seems to be a property of empty space itself, a kind of energy intrinsic to the vacuum. The most natural explanation is that dark energy is the cosmological constant, a term Einstein added to his equations and later called his greatest blunder. But the value of the cosmological constant suggested by observations is far smaller than quantum field theory predicts smaller by a factor of 10,120, the largest discrepancy between theory and observation in all of physics. This is called the cosmological constant problem, and we have no solution. Why is the vacuum energy so small? Why is it not zero or enormously large? Why does it have precisely the value needed to cause the observed acceleration? These questions remain unanswered. Dark energy is something we observe but do not understand, a placeholder name for our ignorance. It makes up about 68% of the total energy content of the universe, dominating everything else, yet we know almost nothing about it. The acceleration of the universe has profound implications for the future. As the expansion accelerates, distant galaxies will recede from us faster and faster, eventually exceeding the speed of light in terms of recession velocity. This does not violate relativity. The galaxies are not moving through space faster than light, but space itself is expanding between us and them. Light from these galaxies will become increasingly redshifted, stretched to longer and longer wavelengths as it travels through expanding space, until eventually it becomes undetectable. Galaxies will disappear over the cosmic horizon, their light unable to reach us because space is expanding too fast. Trillions of years in the future, if the acceleration continues, our galaxy and the local group of nearby galaxies will be completely isolated. All other galaxies will have receded beyond the cosmic horizon. An observer in that distant future, looking up at the night sky, would see only the stars of their own galaxy and a few nearby satellite galaxies. The rest of the universe would be invisible, beyond reach, as if it didn't exist. They would have no way to discover that the universe is vast and filled with billions of galaxies. The evidence of cosmic expansion would be erased. The universe would appear static and small. This is a humbling thought. We live in a special time, cosmologically speaking, when the evidence of the universe's true nature is still visible. In the far future, that evidence will be gone, and civilizations arising then might never discover the Big Bang or cosmic expansion. They would have a fundamentally incorrect picture of the universe because the evidence would no longer be accessible. This suggests that we should not be too confident about our current understanding. There might be aspects of the universe that are no longer visible to us, evidence that existed in the past but has been erased by cosmic evolution. Consider the deep future of the cosmos, the long, slow twilight that awaits the universe over timescales that dwarf its current age. Stars will continue to form for trillions of years, but eventually the gas needed to make new stars will be exhausted or locked up in dead stars and remnants. Star formation will cease. The universe will enter what is called the degenerate era, dominated by dead stars, white dwarfs, neutron stars, black holes, slowly cooling in the darkness. Over even longer time scales measured in googolls of years, protons themselves might decay, breaking down into lighter particles and energy. If this happens, even the dead stars will eventually evaporate, leaving behind only black holes and diffuse radiation. The black holes themselves will evaporate through, hawking radiation over timescales so long they are almost meaningless, 10,100 years or more, for supermassive black holes. Eventually, the universe will consist of nothing but a thin, cold bath of photons and other particles, spread across ever-expanding space, approaching absolute zero in temperature. This is the heat death of the universe, the ultimate equilibrium state where all useful energy has been exhausted, where no work can be done, where nothing interesting can happen. It is not a dramatic end like a big crunch or big rip, but a slow fading into darkness and cold, asymptotically approaching, but never quite reaching a state of perfect emptiness. This fate seems melancholy, but it is also peaceful, a gradual return to simplicity, a release from the complexity and struggle of existence. Yet even this far future is uncertain. We don't know if protons decay. We don't know if dark energy will remain constant or change over time. We don't know if there are cycles of expansion and contraction. We don't know if quantum fluctuations might eventually produce new big bangs in isolated regions of space, spawning new universes billions or trillions of years in the future. Our knowledge extends only so far, and beyond that lies genuine uncertainty about the ultimate fate of everything. There is something oddly comforting about this uncertainty. The universe is not a closed book whose ending we can predict with certainty. It remains mysterious, open to possibilities we haven't imagined. Our current theories are provisional, our best guesses based on limited evidence. The universe has surprised us before with dark matter, with dark energy, with quantum mechanics, with relativity. It will likely surprise us again. The secrets of the cosmos are not exhausted. There are deeper layers of understanding waiting to be discovered. Let your mind rest now on the concept of deep time, the vast spans of past and future that extend beyond human comprehension. When we think about time, we naturally think in human scales, days, years, lifetimes. A century seems like a long time. A millennium is hard to grasp, but the universe operates on time scales that make millennia seem like eye blinks. The sun will shine for another 5 billion years. The galaxies will continue their slow dance for trillions of years. Black holes will evaporate over googolls of years. These numbers are so large that they lose meaning, becoming abstract rather than visceral. Yet there is value in attempting to grasp these timescales and letting our minds stretch toward the cosmic perspective. When we do, our everyday concerns gain a different flavor. The things that seem so urgent and important shrink to their proper scale. This is not to say they don't matter. Your life matters to you, and that is enough, but rather to place them in context. You are a brief flicker of consciousness in an ancient and vast universe, a temporary organization of atoms that were here long before you and will be here long after, rearranged into new forms but never destroyed. This perspective can be either nihilistic or liberating, depending on how you hold it. If nothing we do matters on cosmic scales, why do anything? But this reasoning confuses scale with significance. Things can matter locally without mattering cosmically. Your actions affect you and those around you. They shape your life and the lives of others. The fact that these effects don't ripple out to affect distant galaxies doesn't make them meaningless. Meaning is local and personal, not cosmic and absolute. There is also beauty in impermanence. The stars shine for billions of years, but eventually they die. Galaxies collide and merge, forming new structures. Even the universe itself had a beginning and will have an end, or at least a transformation into something unrecognizable. Nothing lasts forever. Everything is temporary, including the cosmos itself. This impermanence is not a flaw, but a feature. It allows for change, for evolution, for novelty. A perfectly static universe would be dead and boring. It is the flux, the change, the transformation that makes existence interesting. Consider the night sky one more time, that ancient sight that has captivated every human culture. Our ancestors looked up at the same stars, though in slightly different configurations, and wondered. They created myths to explain the patterns, stories to make sense of the cosmos. They had no telescopes, no understanding of physics, no knowledge of galaxies and black holes and dark energy. Yet they felt the same sense of awe and mystery that we feel today. The cosmos has always been a source of wonder, a reminder that we are part of something larger than ourselves. Modern science has not diminished this wonder, it has deepened it. We now know that the stars are not painted on a celestial sphere, but are distant suns, some with planets of their own. We know that the faint band of the Milky Way is our view from inside our galaxy, looking through the disk. We know that the universe extends billions of light years in all directions, filled with hundreds of billions of galaxies, each containing hundreds of billions of stars. The scale is almost incomprehensible, yet we have measured it, mapped it, begun to understand it. And we have discovered not just the vastness of the universe, but its strangeness. Quantum mechanics tells us that reality at the smallest scales is fundamentally probabilistic and weird. Relativity tells us that space and time are not absolute, but relative, that gravity is the curvature of space-time itself. Dark matter and dark energy tell us that most of the universe is invisible and mysterious. Black holes tell us that there are regions of space-time from which nothing can escape. The cosmic microwave background tells us that the universe had a beginning, a moment of creation from which everything emerged. These discoveries are astonishing, yet they also raise new questions. We have solved some mysteries only to encounter deeper ones. We understand the large-scale structure of the universe, but we don't know what dark matter is. We can describe how gravity works, but we can't reconcile it with quantum mechanics. We know the universe is expanding, but we don't know why it exists at all. Every answer leads to new questions. Every solution reveals new problems. The universe is not a puzzle we will ever completely solve, but an endless source of mystery and wonder. And perhaps that is as it should be. If we could understand everything, if the universe held no more secrets, what would be left to discover? The mystery is not a failure of science, but its fuel. It is what drives us to build bigger telescopes, to design more sensitive detectors, to develop new theories, and test them against observation. The universe challenges us to understand it, to push the boundaries of knowledge, to reach beyond what we currently know. As you drift towards sleep tonight, let these thoughts wash over you gently. You are made of stardust, atoms forged in the hearts of long-dead stars. You are the universe becoming conscious of itself, a temporary organization of matter and energy that can contemplate its own existence. You are connected to everything, every atom in your body, linked through cosmic history to the Big Bang and to distant galaxies. You are part of something vast and ancient and mysterious, something that has been unfolding for billions of years and will continue for billions more. The secrets of the universe are patient. They have waited 13.8 billion years, and they can wait a little longer. They will still be there tomorrow, still mysterious, still beautiful, still calling to us to understand. But for now, for tonight, it is enough simply to appreciate them, to let their gentle mystery lull you into rest. The cosmos is vast, and you are small, but you are part of it, and that is enough. Sleep well under the ancient light of distant stars, part of the eternal dance of matter and energy that we call the universe.